Another word that you've probably heard of in everyday life is electrolytes. And they've probably just seemed like something that belonged in Gatorade to you. It's something that just somehow makes you better at sports. And that's really not what electrolytes are. I mean, they are, but not intentionally. Electrolytes are going to be things like salts that can dissolve in water. And because your body needs those salts, it does end up having a performance helping effect when it comes to athletics. But that's not what the intent of the word is. So if you have an ionic compound, and let me beat on the most dangerous pair of words that you'll find for a lot of chemistry. If it dissolves and dissociates in water, then you're going to have ions that are present in the water. Now, that is an electrolyte. An electrolyte is anything that you can dissolve in water, and once it's dissolved, it separates into ions. Dissolves into water, dissociates into ions. If it dissolves and dissociates, you've got an electrolyte. Acids are electrolytes, bases are electrolytes, table salt is an electrolyte. Anything that dissolves and dissociates into ions in solution is going to be an electrolyte. So, good news for those of you who like gummy worms. If they're the sour gummy worms, those have electrolytes too. You've got the citric acid in there, and the citric acid is going to be an electrolyte. So, have fun with those gummy worms. Now, let me point out something else though. Before we ever have both things together, we don't have an electrolyte, and as a result, there's nothing there that can actually carry a charge if you were to try to pass electricity through. So what you see in this set of pictures here, this is deionized water, heavily deionized water, carefully deionized water. So there are no ions present. All you have are totally neutral water molecules. And this is a live wire sitting in the water. Nothing is happening with this light bulb. It's not glowing because no charge is being carried between these two wires. There's no ions present. I don't recommend that you suddenly stick your finger in this either, because your finger has plenty of electrolytes on it, which will immediately dissolve and dissociate and immediately start carrying that charge, and you will immediately be getting fried. Now, let's contrast that. What if we had lots and lots of ions, but they were not dissolved or dissociated? This is just a pile of table salt, and we've immersed the electrodes in it. Now, we know that it's filled up with these positive and negative charges, right? But remember, when it's a solid and it's not dissolved, they're sticking tightly to each other. There's no movement going on there, at least no meaningful movement going on, and there certainly isn't enough to carry a charge between these two electrode wires. So again, it's going to be insulated. However, when you put water in it, now the negative ions can shoot over here to the positive electrode. The positive ions can shoot over to the negatively charged electrode. And I'm speaking about charge here. When you get to electricity, you'll find out there's a whole bunch of extra notation and oddness in the sign conventions there, but we're going to skip that. We're talking about chemistry right now. The negatively charged ions move toward the positively charged electrode. Positively charged ions move toward the negatively charged electrodes, and by doing that, they create a charge imbalance, and that helps carry the current. So if you're standing in salty water and lightning hits, it can carry the electricity very easily. If you're standing in a perfectly insulated pile of salt, other than the fact you're going to get desiccated and turn into a mummy, you would be well protected from the lightning. But the moment it starts to rain, you're probably going to get fried again.